So here I will give a brief walkthrough of my code resolution for programming challenge 4. So for this challenge, I have created 2 classes to accommodate all the interface methods that I wanted to implement it. So interface methods are add input RE, which stands for regular expression. Get grammar will return the grammar object. Grammar productions will return only the productions from the grammar object. And get languages will return the curly braces, a curly braces formatted language that easy for a human to understand what language is associated with the regular expression. And the last 2 methods is get NFA and get DFA, which stand for non-deterministic finite automata and deterministic finite automata. So before I dive into the code, here's my logic of how to construct a finite state automata from a regular grammar. So the code will read a regular expression, and from the regular expression, it will construct the equivalent regular grammar. And once it has the regular grammar, then it use the FSM class to construct the finite state table. So the logic from converting a grammar to a finite state table is to accommodate the 3 different forms a regular grammar has. So basically for a regular grammar, it has these 3 different forms of production. So for each production here, the code will loop through the productions and add the using the add transition method to add a from state to a to state based on the input symbol, which is a terminal symbol. And also for any start symbol S, it defaultly the FSA class will add a start state S0, and for all the terminal symbols, it will defaultly add a final state, which will be SA. And for non-terminal symbols, it will add a SA to represent them. All right, so let's dive into the code. As usual, as in previous my code, I import these 2 modules. So I import these 2 modules here as well. So the first class is called recognize-re. So for this class, when it's getting instantiated, it will have 2 properties here that has a default value. And then the user will be able to call this add input re method to add a regular expression to the instance. And then the user will be able to call get grammar. That this logic implemented here is converting a regular expression to a grammar. So a note to you that for my code here, it can only parse particular regular expression pattern. So the specific pattern I add in the comment here, that it can only The regular expression can only have one U, no parentheses, and can only have one star. So, and a good example is I listed here. Yeah, this is the limitation of my code right now. So in order for this piece of code to parse or to be able to read more complex regular expression, in the future work, I will need to add recursive method here to be able to parse multiple use or a regular expression has parentheses that group multiple symbols together, and also it may have multiple star in the regular expression. Yeah, so that's my limitations for now. So this implementation here is a split, as it can only accept one U. So I use a split method to split the left and right part of the U, and then put a if else block here to see if any side that has the star sign, if it has a star sign, then it means that it has a clean closure here. For clean closure, the code will append an object that the object key is the eventually will be represented as the left side of the grammar production, and the value to the key will be the right side of a grammar production. So you'll see that my grammar structure here has a B vocabulary that default to has two elements, as the start symbol and A as the non-terminal symbol. And T represents the terminal symbols will be associated with a empty list, and S and P will be a empty list, but P will eventually represent a list of production. And the languages. This languages is actually a property that will be used to get the human readable language that equivalent to the regular expression. So here, so this if else block is eventually adding more value to this grammar dictionary / object, and then at the end it returns its grammar object. And the next method that a user will be able to call it is the get grammar productions. So this one is reads from the grammar that get constructed in the previous method, but only reads at the P key. And the value for that key, it will get the left side first and then get the right side. And here the if else block is just to accommodate how I want to present final productions. So the final productions that gets returned is a long string. The languages here is that it will read the languages key from the languages property from the grammar dictionary, and make sure that if it has a infinite or it has the definite. So infinite actually means it's a clean closure, and definite means that it could be a concatenate string. So this function also returns a string type response to the user. All right, so now this one, the last two methods, is the core method that how this grammar will get converted to a finite state tables. So these two methods will essentially call the method inside of this FAC class. Let's firstly look at the get NFA one. So get NFA is to get the non-deterministic type or the finite state table. And for this typically for this one, a first thing needs to call this FAC class to get instantiated a instance from this class, and then they call this add final state, add start state, and add input. All these three chainable methods to get this instance ready to be parsed. And then this whole block of code here actually represent the implementation details of the logic I stated here. So basically for these three forms of type, this block has if, else, and else, three conditional checks that make sure to convert this grammar productions to a correct transition type. And then at the end, it will call the get method and return it. And the next method, get DFA, is expected to be called after this get NFA called or finished execution. But I do have this check here to make sure if the user didn't call this one firstly, it will make sure to call this first because it has a bunch of implementation details that convert grammar to from grammar productions to transitions. All right, so move on. Let's look at this class FSA. So I remember in my last programming challenge, I also create a FSA class that will convert a non-deterministic type table to a deterministic type table. So for this challenge, I referenced my previous code, but I did do a little bit of modification. So the modification I made here is that I added this additional property for the instance that I instantiated from this class. So this property is used to because we know that from the grammar we can't like for this add transition method, when those transition method gets called, you cannot guarantee that each transition will fulfill the entire state table. That for instance for this one, it actually it may doesn't have like, for example, if it only have for this regular expression here, it is actually, the test I'm going to run for this one. The entire code is this one. So for this test, it has two type of regular expression. So either it is any number of 0 or it could be just a string, which is 0, 1. So for this add transition here, if the right side only has like any number of zeros, then it will miss the other input symbol, which is the 0, 1. So For this class, I added this fmap array. And also I added this additional parse fmap array method that reads from the transition, all the transitions, and make sure that all the transition for the table, all the for each transition, that if the for any input symbol, like for the test example, if it misses one specific value for one specific input symbol, I will I think there is a hold on, let's see. Parse fmap array. Yeah, here, this one. So I make sure that it's get fulfilled. It's not a non-type. It has to be a empty string that when this method get finished execution, it will create a full picture of fmap. And then for this fmap, this parse method will be able to parse this fmap into a list that could be used within a data frame from the pandas module. Yeah, so this additional method, this additional property for on the class, and I think that's it. Oh, the other part is the same as my previous code FSA class. Okay, so now after we define these two classes, how do we gonna test the functionality? So firstly, I need to call this class, get an instance, and then, as I mentioned before, I test this string that is satisfied my code that only have one U, only have one star, doesn't have any parentheses. So I call this at input RE to input the regular expression here. And then get grammar, so it output the entire grammar dictionary here. So it has a vocabulary, has the S, A, 0 and 0, 1. So these two are the terminal symbol. And S is the star symbol. The production here, 1, 2, 3, 4, 5, 6. It has 6 productions. That when you call get grammar productions, it can also put it like a more readable format here. And then get languages. It will get you a human readable language that is equivalent to this regular expression. This means that this regular expression could equals to that any number of zeros or just a string of 0, 1. And then call this get NFA, which will be the non-deterministic state table, and call get DFA will return the deterministic type state table. So in order to prove that these two tables is equal, so I give this two test cases that I'm going to walk through the state table to see if the state table could give me the same result, if it's recognizable or not. All right, so for 0, 1, if we look at this non-deterministic table, 0, 1 means that it could be start from 0, 1 here. A start state from S here, S0, and then on the input 0, 1, it goes to here, and then it goes to S8. S8 indicates that it's a final state, then which means this string is recognizable. And then the same string for this deterministic type table. So let's see, starting from S0, giving an input of 0, 1 here, it also goes to SF, indicated as a final state. Right, so this string for both table, it all goes to a final state, which means both table can recognize this string. And then if we test this 5 zeros string, similarly, starting from S0 for this table, it goes to, on 0, it goes to SA or SF. SF means it's a final state. And SA means that on SA, on input 0, it goes to SA or SF. So if we assume that the 0, on 0, all the transition goes to, all the non-last transition goes to SA, and the very last transition goes to SF, then this string is recognizable for this type, for this table. And then let's look at this table. For all zeros here, starting from S0 on input 0, it goes to this combined state of SASF, and the combined state of SASF goes to SASF as well on input 0. So for this string, for this type of table here, it always goes to a combined state of SA and SF, which means that it could be also recognizable. All right, so here, that's all of my explanation of my code solution for this programming challenge. Thank you.